This is the EdExcel A-Level Further Maths Paper 3, covering the Further Mechanics 1 module. And this paper is from the 2022 series. Question number 1. A particle A of mass 3m and a particle B of mass m are moving along the same straight line on a smooth horizontal surface. The particles are moving in opposite directions towards each other when they collide directly. Immediately before the collision, the speed of A is ku and the speed of B is u. Immediately after the collision, the speed of A is v and the speed of B is 2v. The magnitude of the impulse received by B in the collision is 3/2 mu. For part A, we have to find v in terms of u only. Well, in this question, it would help if we draw a diagram. So for part A, we've got particle A with mass 3m and particle B with mass m. Before the collision, the speed of A is ku and the speed of B is u. Notice they are moving towards each other. Now after the collision, A has a speed of v and B has a speed of 2v. Now the problem is we don't know if after the collision they move in the same direction or in opposite directions. So the speed of A after the collision would still be v, but in the opposite direction. So they could either move in the same direction after the collision or in opposite directions after the collision. And we are told that the magnitude of the impulse received by B in the collision is 3/2 mu, and that's shown here, and we would have an equal and opposite impulse received by A, 3 mu/2. So now to work out the value of v in terms of u only, well, let's think about impulse equaling the mass multiplied by the change in velocity. And let's concentrate on B only for this. So if we concentrate on B, we have the impulse 3 mu/2. This is equal to the mass m multiplied by the change in velocity, so this will equal 2v subtract, well, we would subtract negative u because it's going in the opposite direction, so we subtract negative u. And from this, we can find out what v is in terms of u. So we have 3u/2 equaling 2v plus u. Subtracting u from both sides, we would have u/2 equaling 2v, and therefore dividing through by 2, we would end up with v equaling u/4. For part B of the question, we have to find the two possible values of k. Now, we've got one option where v is pointing to the right after the collision, or v is pointing to the left after the collision. So we've got two options here. And if we take right as positive, again, using impulse equals mass times by the change in velocity, for A, we would have the impulse minus 3 mu over 2 equaling 3m, which is the mass, multiplied by, well, we have v subtract and then ku. So, noticing the 3 m's on both sides cancel, we would have minus u over 2 equals v subtract ku. Now, we have already worked out what v is, that's u over 4. So we have minus u over 2 equals u over 4 subtract ku. So we would have minus 1/2 equals 1/4 subtract k. One option for the value of k is therefore equal to 3/4. Let's consider the second option then. For A, we would have the impulse negative 3 mu over 2. This is equal to the mass 3m multiplied by, well here, if v is pointing to the left this time, we would have minus v, then subtract ku. So, noticing that the 3m's cancel on both sides, we would have minus u over 2 equals minus v minus ku. And we already know what v is. That is given by u over 4. So we've got minus u over 2 equals minus u over 4 minus ku. And noticing that the u's cancel everywhere, we would have then minus 1/2 equals minus 1/4 minus k. And noticing that the minuses cancel everywhere, we would have 1/2 equals 1/4 plus k, which means if we solve for k, k would equal 1/4. So we've got two possible values of k, 3/4 and 1/4. Question number 2. A van of mass 600 kilograms is moving up a straight road which is inclined at an angle alpha to the horizontal, where sine alpha is equal to 1/15. The van is towing a trailer of mass 150 kilograms. The van is attached to the trailer by a tow bar which is parallel to the direction of motion of the van and the trailer, as shown in figure 1. The resistance to the motion of the van from non-gravitational forces is modelled as a constant force of magnitude 200 newtons. The resistance to the motion of the trailer from non-gravitational forces is modelled as a constant force of magnitude 100 newtons. The tow bar is modelled as a light rod. The engine of the van is working at a constant rate of 12 kilowatts. We've defined the tension in the tow bar at the instant when the speed of the van is 9 meters per second. So, here we've got all the relevant forces shown on the diagram. We've got the driving force D, the resistance force to the van 200 newtons, the resistance to the trailer 100 newtons, we've got the tension, we've got the weight of the trailer 150 g, the weight of the van 600 g. So the first thing we can do is find out this driving force. And we can find out the driving force because we know the power and we know the speed. So if we consider P equals driving force times by V, then we've got the power 12,000 watts and this is equal to the driving force, which is D, multiplied by V, which is 9. And so therefore, if we attempt to solve for D, you will find D to equal 12,000 divided by 9, which is 4,000 over 3. So therefore, we have D, which is equal to 4,000 over 3. Using the sum of the forces is equal to the mass times the acceleration for the whole system, we can find out the acceleration, and then from that we can consider either the van or the trailer to find out t. So if we consider the sum of the forces equals mass times the acceleration, well, we've got going forward d, which is 4,000 over 3, and then we subtract from this. Well, we've got the 200 and this 100 which we need to subtract, So we subtract the 200 and then we would also subtract the 100, and what we would also subtract is the component of the weight parallel to this slope. So the component of the weight parallel to the slope for the van will be 600 G. So we subtract 600 G multiplied by sine alpha and then we subtract the 150 G sine alpha, and this is equal to the total mass 600 plus 150, which is 750, multiplied by the acceleration A. So, simplifying even further, what we would have is 4,000 over 3, subtract 200, subtract another 100, that's 3,100 over 3. And then 600 G and the 150 G can be combined to give 100. Well, here we would have 750 G, and then sine alpha is 1 over 15, so we would multiply by 1 over 15, and this is equal to 750 A. So I need to take away 750 times 9.8 times 1 over 15. So we end up with 1,630 over 3, which is equal to 750 A. And from this we can conclude the value of A is equal to, well, if I divide this by 750, we would get 0.724, etc. meters per second squared. And now to find out what the tension is, we can consider F equals ma for the trailer. So for the trailer, well, we've got the tension going forward, T, and then we subtract from this the 100 newtons, and then we would also subtract the weight of the trailer parallel to the slope. So we subtract 150 G sine alpha, and this is equal to the mass 150 multiplied by the acceleration. Well, it would accelerate at 0.724 etc. meters per second. And we know what sine alpha is, that's 1 over 15. So we've got t, subtract 100, subtract 150g multiplied by 1 over 15, and this is equal to, well, if I multiply this acceleration by 150, we would get 326 over 3. So now we can find out what t is. So if we attempt to solve for t, what we need to do is add on 100 and then add on 150 times 9.8 times by 1 over 15. So we get 307 newtons given to 3 significant figures. Question number 3. A particle P of mass 0.5 kilograms is moving in a straight line with speed 2.8 meters per second when it receives an impulse of magnitude 3 Newton seconds. The angle between the direction of motion of P immediately before receiving the impulse and the line of action of the impulse is alpha, where tan alpha is 4/3 as shown in figure 2. We have to find the speed of P immediately after receiving the impulse. Well, if we know that tan alpha is 4/3, we can form a 3, 4, 5 right angle triangle and find sine alpha to be 4/5, cos alpha to be 3/5, and tan alpha given as 4/3. Now, with this question, we can find out what the impulse is in terms of its components. So the impulse I, that's equal to 3 times by cos alpha I plus 3 times by sine alpha j. Now, what we have over here, I, is 3 multiplied by 3/5 in the I direction plus 3 multiplied by 4/5 in the j direction. So 3 times by 3/5 is 1.8. So therefore I is equal to 1.8 I plus, now here we've got 3 times by 4/5, which is 2.4. So we've got I equals 1.8 I plus 2.4 j. And now to find out what the speed is after receiving this impulse, well, we can use the impulse is equal to the change in momentum, and the change in momentum is equal to the mass multiplied by the change in velocity. So we have the impulse 1.8 I plus 2.4 J, and this is equal to the mass 0.5 multiplied by the change in speed. So if we say that the speed after is v as a vector, and then we subtract, well, here before we have 2.8 I plus 0j, so we subtract 2.8 I. So if we multiply through by 2, we would have 3.6 I plus 4.8 J equals V subtract 2.8 I. So we can find out what V is. V is equal to, well, we have 3.6 plus 2.8, which is 6.4. So we have 6.4 I, and then we add on 4.8 J. And therefore, to find out what the speed is, we take the magnitude of this vector. So we have 6.4 squared plus 4.8 squared, and then square rooted. So we have 6.4 squared plus 4.8 squared, then all square rooted, and it turns out the speed is given by 8 meters per second. Question number 4. Two smooth uniform spheres A and B have equal radii. The mass of A is 3m and the mass of B is 4m. The spheres are moving on a smooth horizontal plane when they collide obliquely. Immediately before they collide, A is moving with speed 3u at 30 degrees to the line of centers of the spheres, and B is moving with speed 2u at 30 degrees to the line of centers of these spheres. The direction of motion of B is turned through an angle of 90 degrees by the collision, as shown in figure 3. So that's what we see here. 30 degrees plus the 60 degrees gives this 90 degrees. For the first part, we have to find the size of the angle through which the direction of motion of A is turned as a result of the collision. So if I consider the conservation of linear momentum parallel to the line of centers, well, we've got the situation before equaling the situation after. So I've got the mass of A, which is 3m, and then I need to multiply that by the speed. Well, here I would have 3u cos 30. And then we add on, well, considering B before, I've got the mass 4m, and then I need to multiply this by the speed. Well, parallel to the line of centers, I would have 2u cos 30, but because the arrow is pointing to the left, I would have to multiply by minus 2u cos 30. And the situation after, well, if here we've got an angle of theta, and then here we've got x, say, and here we've got y, say, then the situation after, I would have the mass of A, 3m, multiplied by, well, here I would have the component parallel to the line of centers, x cos theta, but because the arrow is pointing to the left, here I would have minus x cos theta, and then I would add on 4m multiplied by y cos 60, the component parallel to the line of centers. Now, recognizing that the m's cancel everywhere, well, first of all, cos 30 is equal to root 3 over 2, and I'm multiplying that by 9, so I would have 9 times by the square root of 3 multiplied by u divided by 2, subtract, well, here I have root 3 over 2 times by negative 8, so that will be 4 times by the square root of 3 multiplied by u, and this is equal to, well, here we have negative 3x times by cos theta, and then cos 60 is a half times by 4 is 2, and then we multiply that by y, so we add on 2y. Now, 9 root 3 over 2 subtract 4 root 3, that's just going to equal root 3 over 2, and I multiply that by u, and this is equal to negative 3x times by cos theta plus 2y. We'll call this equation 1. Now, we can find out what theta is, and to do that we need to consider the situation perpendicular to the line of centers. And here we need to recognize that the perpendicular components will remain unchanged. And so, perpendicular to the line of centers, well, if I consider particle A, I've got 3u sine 30 and that will equal x sine theta. And so what we will end up with over here then is x sine theta is equal to 3u over 2. Let's call this equation 2. And if we consider b, then we would have 2u sine 30 and that's equal to y sine 60. And so if we tidy this up even further, what we will end up with is, well, if I do 2 sine 30 divided by sine 60, I get 2 root 3 over 3, which means y will equal 2 times by the square root of 3 over 3. So we'll call this equation 3. Now, ultimately we want to find out what theta is, and that will enable us to find the deflection. So, for us to find out what theta is, well, I need to somehow eliminate x and y in equation 1. So, if I take a look at equation 2, where I've got x sine theta equals 3u over 2, what we can do is rewrite this equation such that we have x equals 3u over 2 sine theta. And what we will do now is substitute in 2 and 3 into 1. So 2 and 3 into 1. Well, from equation 1 we've got root 3 over 2u and this will equal, well, what I've got is negative 3x cos theta, so I would have negative 3 multiplied by 3u over 2 sine theta multiplied by cos theta, and then we would add on, well, here I would have 2y, so we add on 2 multiplied by 2 root 3 over 3u. So now let's simplify all this. Well, the u's cancel everywhere, so I will be left with root 3 over 2 equals, well, here I have minus 9 over 2 multiplied by cot theta, and then I add on 4 root 3 over 3. So let's rearrange for cot theta. Cot theta is equal to, well, here I have 1/2 root 3 subtract 4 over 3 root 3, and then if I divide that by minus 9 over 2, what you will find then is cot theta is equal to 5 root 3 over 27. So if I times this by root 3 and then do 1 over this, we will therefore find tan theta to equal 9 root 3 over 5. And therefore, taking the inverse tangent of this, you will find theta to equal 72.216, etc. So now that we know what theta is, we can now find out the deflection angle. Now, for the deflection angle, we do not add 30 to theta. Instead, what we do, well, if I extend this line over here, what we do instead is find out what this angle here, alpha, is. This will be our deflection angle, the angle between the original u and the new x. So, alpha then is equal to 180, subtract this 72.216, etc. Subtract 30 degrees. So if I do 180, subtract this, subtract 30, what we end up with is an angle of 77.78, etc. And from this then, we can conclude we have a deflection by an angle of 78 degrees to two significant figures. For the next part, we have to find in terms of m and u the magnitude of the impulse received by B in the collision. So, we know that impulse is equal to the change in momentum, which is equal to the mass times by the change in speeds. So the magnitude of the impulse, we'll call this I. This is equal to, well, if I go back to the diagram, and if I consider B, well, I've got my mass 4m. So, we have 4m being multiplied by y cos 60, subtract, and then negative 2u cos 30. So, we have 4m being multiplied by, well, y cos 60, well, I already know what y is, that's 2 root 3 over 3. So we have 2 root 3 over 3 u multiplied by cos 60, which is 1/2, plus 2u multiplied by, well, cos 30 is root 3 over 2. So, we have 4m being multiplied by, well, here I've got 2 over 3 root 3 plus another, well, I'm going to times this by 1/2 and then add on root 3. So I've got 4m times by 4 root 3 over 3u, and therefore the magnitude of the impulse we would have 4 times by 4, which is 16, and then I've got the root 3 over 3, then I've got mu Newton seconds. Question number 5. Two particles P and Q are moving in opposite directions along the same straight line on a smooth horizontal surface when they collide directly. The mass of P is 3m and the mass of Q is 4m. Immediately before the collision, the speed of P is 2u and the speed of Q is u. The coefficient of restitution between P and Q is e. For part A, we have to show that the speed of Q immediately after the collision is u over 7 multiplied by 9e plus 2. So we've got P and Q shown here. We've got the speed of P 2u before and the speed of Q u before. The speed of P after is v sir, and the speed of Q after is w sir. And we know that the situation before, the particles P and Q are moving towards each other, indicated by those arrows. Now, what we can do is find out what the speed of Q immediately after the collision is by considering Newton's law of restitution and conservation of linear momentum. So if I consider the conservation of linear momentum, I have 3m multiplied by 2u plus 4m multiplied by negative u. This is equal to (3m) multiplied by negative v plus 4m multiplied by w. Now, the m's cancel everywhere, so we are left with 6u subtract 4u, so that's 2u. And that will equal, well, here I've got negative 3v plus 4w. Now, we can use Newton's law of restitution. We've got E, which is equal to the speed of separation divided by the speed of approach. So they would separate with speed w plus v, because we've got w subtract negative v. And the speed of approach will be 2u plus u. So we can see from here then, w plus v equals 3eu. Now we can solve this equation, we'll call it 1, simultaneously with this equation here. And to do that, what we can do is multiply equation 2 by 3, leaving us with 3w plus 3v equals 9 EU. Now we'll call this equation 3. And now what we will do is add together equation 1 and equation 3. This will eliminate the v's. So if I add together equation 1 and equation 3, well, we've got negative 3v plus 3v, that's 0v. Then we've got 4w plus 3w, that will be 7w. and this is equal to 2u plus 9eu. And what we can do is factorize out a u from the right hand side. So I've got 7w equals u multiplied by 9e plus 2. And then if I divide through by 7, we can therefore conclude the speed immediately after the collision for q, which is w, is equal to u over 7 multiplied by 9e plus 2. And what we'll do is we'll call this equation 4 for now. Then, after the collision with P, particle Q collides directly with a fixed vertical wall and rebounds. The wall is perpendicular to the direction of motion of Q. The coefficient of restitution between Q and the wall is a half. We have to find the complete range of possible values of E for which there is a second collision between P and Q. Now, what we need to do is find out the speed of P after the collision. So what we need to do is find out what V is. And we can do that by using equation 2. We will substitute in equation 4 into equation 2. So 4 into 2, we have W, which we know is U over 7 multiplied by 9e plus 2 plus V. This is equal to 3 EU. So I've got 9 EU over 7 plus 2U over 7 plus V equals 3 EU. So to find out what V is, well, 3 EU subtract 9 over 7 EU, that will be 12 EU over 7. So we have V equals 12 EU over 7 subtract 2U over 7. And if I factorize out a U over 7, we can therefore conclude V is equal to U over 7 multiplied by 12e minus 2. Now, what we can do now is find out if there's going to be a second collision. Well, we know the speed of V. Now, if we've got a wall over here, what's happening is it's rebounding with speed x, say. And we know that the coefficient of restitution between the particle and the wall is a half. So if we were to use Newton's law of restitution, we've got E, which is 1/2, which is equal to the speed of separation, x, over the speed of approach, which we said was w. X is equal to w over 2, and so we know what w is, that's u over 7 multiplied by 9e plus 2, and if I divide that by 2, you will find x to equal u over 14 multiplied by 9e plus 2. Now, for a second collision, x must be greater than v. So, we've got x, which is u over 14 multiplied by 9e plus 2 we're expecting this to be greater than x, which is u over 7 multiplied by 12e subtract 2. And if I rewrite this, so we've got a denominator of 14, we would have u over 14 multiplied by 9e plus 2. This is greater than 2u over 14 multiplied by 12e minus 2. So we've got 9e plus 2 being greater than 12e minus 2. So we have, if we simplify this, well, this needs to be multiplied by 2, so we've got 24e minus 4. So we have 6, which is greater than 15e, which means 2/5 is greater than e, and therefore the range of values for e, we've got 0, which is less than e, which is less than 2/5. Question number 6. Two blocks A and B of masses 2 kilograms and 4 kilograms respectively are attached to the ends of a light inextensible string. Initially, A is held on a fixed rough plane. The plane is inclined to the horizontal at an angle theta, where tan theta is 3/4, and because of that we can form a 3, 4, 5 right angle triangle and see that sine theta is 3/5, cos theta is 4/5, and tan theta is 3/4. Now the string passes over a small smooth light pulley P that is fixed at the top of the plane. The part of the string from A to P is parallel to a line of greater slope of the plane. Block A is held on the plane with the distance AP greater than 3 meters. Block B hangs freely below P at a distance of 3 meters above the ground, as shown in figure 4. The coefficient of friction between A and the plane is mu. Block A is released from rest with the string taut. By modelling the blocks as particles, for part A we have to find the potential energy lost by the whole system as a result of B falling 3 meters. Well, the total loss in GPE is equal to the loss in gravitational potential energy by B, subtract the gain in gravitational potential energy by A. So if I consider the loss in GPE by B, well, it starts off with gravitational potential energy of 4g multiplied by 3, and then it finishes at the ground. So the loss in GPE will be 4g multiplied by 3, and then we subtract from this the gain in GPE from A. So with A, well, if B has fallen by 3 meters, that means A has moved up by a distance of 3 sine theta, and that's vertically upwards. And then I multiply that by the mass times by gravity. So I subtract 2g multiplied by 3 sine theta. Now I know what sine theta is. That's 3/5. So what we have then is 4g times by 3 subtract 2g times by 3 multiplied by 3/5. So if I work out what this is, I've got 4 times 9.8 times by 3 subtract 2 times 9.8 times by 3 times by 3/5. And if I work this out, I get 82.32 joules. So I have 82 joules given to 3 significant figures. Now, given that the speed of B at the instant it hits the ground is 4.5 meters per second, and ignoring air resistance, we have to use the work energy principle to work out the value of mu. Now, what we have to do here is use the work energy principle. So, if B hits the ground, well, we know it would hit the ground at speed 4.5 meters per second. And whilst we're here, we've got the weight of B, 4g. We've got the weight of A, 2g. We've got the frictional force F, and we've got the reaction force, which we will call R. So what we can do now is use the work energy principle. So if we use the work energy principle, what we first of all need to do is find out the work done against friction. So for the work done against friction, we've got the frictional force, which is given by F, multiplied by the distance it travels, which is 3. Now, F will equal mu multiplied by R, and then I'm timesing this by 3, the distance it travels. So, I've got mu multiplied by R. Now, R over here, if we go back to the diagram, that will equal 2g cos theta. So I've got 2g multiplied by cos theta, that's what R is, and then I multiply this by 3. So I've got mu times by 2g multiplied by 4/5 multiplied by 3. So I have 24g over 5, which if I work that out, I get 47.04 mu. So that's the work done against friction. And now what we can do is find out the total gain in kinetic energy. The total gain in kinetic energy, we've got 1/2 multiplied by 6, which is the total mass. So this 6 comes from adding together the 2 kilograms and 4 kilograms. And then we multiply this by speed, 4.5 squared. So let's find out the total gain in kinetic energy. I've got 1/2 times by 6 times 4.5 squared. So it turns out we get 60.75. So I've got 60.75 joules for the total gain in kinetic energy. And now what we can use is the total loss in energy is equal to the work done against friction. So we've got 82.32 subtract 60.75, and this is equal to the work done against friction, 47.04 mu. So if I find out what mu is, we've got 82.32 subtract 60.75 divided by 47.04. So it turns out as a fraction we get 719 over 1568. So mu to three significant figures is equal to 0.459. Next, after B hits the ground, A continues to move up the plane but does not reach the pulley in the subsequent motion. Block A comes to instantaneous rest after moving a total distance of 3 plus d meters from its point of release. Ignoring air resistance, we have to use the work energy principle to find the value of d. Well, what we'll do is we'll consider A. Now, what's happening is, we know that block A comes to instantaneous rest. So when the block is over here somewhere, we know it's moved 3 meters, but then as this hits the ground, okay, because it's moved the 3 meters, block A is still moving to a point over here where it comes to instantaneous rest, and here it's moved a distance of d. Now when it's over here, its speed is 4.5 meters per second, and when it's here, its speed is 0 meters per second. It comes to instantaneous rest. So what's happened is, it's gained potential energy, but it's lost kinetic energy, and it's also done work against friction because the plane is rough. So, with all that in mind, the loss in kinetic energy then is 1/2 times by 2 times by 4.5 squared. So if I work out what this is, we get 20.25 joules. And we also know it gains potential energy. So the gain will be the mass 2 times by g times by sine theta multiplied by d. So we have 2g multiplied by d multiplied by 3/5, and if I work this out, I get 11.76 d. joules. And now I can also find the work done against friction, and this will equal the frictional force F multiplied by the distance it travels, d. So I have mu multiplied by r multiplied by d. Now I know what mu is. I worked that out to be 719 over 1568. So I have 719 over 1568 multiplied by R, which is 2g cos theta multiplied by D. So I've got the 0.458 etc. multiplied by 2g times by 4/5 times by D. So working all this out, I've got this, I've got the 719 over 1568 times by 2 times by 9.8 times by 4/5. So I get 7.19 D joules. So now, if we use the work energy principle, which tells us the total loss in energy is equal to the work done by friction, we've got the 20.25, which was the loss in kinetic energy, subtract the gain in potential energy, which was 11.76 D. This is equal to 7.19 D. So we've got 20.25 equals 18.95 D. And if we find out what D is equal to 20.25 divided by 18.95, which is 1.07 meters. And that's given to 3 significant figures. Question number 7. A spring of natural length A has one end attached to a fixed point A. The other end of the spring is attached to a package P of mass M. The package P is held at rest at the point B, which is vertically below A, such that AB equals 3A. After being released from rest at B, the package P first comes to instantaneous rest at A. Air resistance is modelled as being negligible. By modelling the spring as being light and modelling P as a particle, for party we have to show that the modulus of elasticity of the spring is 2 mg. So here we've got A and B. We've got the natural length being A and the extension when it's at the point B being 2A. In fact, let's show the lengths with double-ended arrows. We've got A and we've got 2A. Now what we need to do is find the modulus of elasticity in the spring. So if we think about the initial elastic potential energy, well, at the point B, we've got lambda multiplied by 2A all squared, and then we divide this by 2A, and it turns out the initial elastic potential energy here will be 2 lambda A, and the initial GPE is equal to 0. Now, if we think about what's happening at A, so it's released from B and it comes to instantaneous rest at the point A. So the final elastic potential energy is equal to lambda multiplied by A squared divided by 2A. So we get lambda A over 2. And if we find the final gravitational potential energy, well, if we take B to be our zero level, when it's at the point A, the final GPE then will be mg multiplied by 3A. So we have 3 mg A. And now what we can do is use the work energy principle. So we've got initial 2 lambda A. This is equal to final lambda A over 2 plus 3 mg A. So 2 lambda A subtract lambda A upon 2, well, that will be 3 lambda A over 2, and the A's cancel everywhere. So we are left with 3 lambda upon 2 equals 3 mg, and therefore multiplying by 2 and then dividing by 3, we can conclude lambda is equal to 2 mg. Next, for the first part of part B, we have to show that P attains its maximum speed when the tension of the spring is half A. Now here we've got our diagram, and we've got this point E where it's in equilibrium, and its maximum speed is here. Now we've got some sort of extension, we'll call it X. We've got the tension in the rope T, and we've got the weight of the particle mg. So we can find out what the tension is. The tension is equal to lambda multiplied by the extension x over the natural length A. And we know what lambda is, that's 2 mg. So I've got 2 mg x over A. And because it's in equilibrium, we would have 2 mg x over A equaling the weight mg. And what we can see then is 2x over A equals 1, and therefore its maximum speed will occur when our extension is equal to A over 2. Now we have to use the principle of conservation of mechanical energy to find the maximum speed, giving an answer in terms of A and G. Now here is a diagram representing what's going on. Initially it's at the point B, then it's released, and then at the end of all the motion it ends up at this point E, and this is where the maximum speed occurs. And what we need to do is use the work energy principle to find out the speed here. And before we do anything else, what we can do is find out this distance here. And the way we can do that is by working out 2a subtract a over 2, which is 3a over 2. So now let's work out the initial elastic potential energy. Well, the initial elastic potential energy at B, well, that will be 2 lambda A and we know what lambda is, that's 2ma. So we have altogether 4 mga. Now at B it's at rest, so the initial GPE is 0 and the initial kinetic energy is 0 if we take B to be our 0 level. Now at the point E, the final EPE, that's equal to lambda 2mg multiplied by, well, the extension here is a upon 2, then this is squared, and then we divide this by 2a. So what this is equal to then is a mg upon 4. Now we can also find the final gravitational potential energy. The final gravitational potential energy is equal to mg multiplied by 3a over 2, which is 3mga upon 2. And the final kinetic energy, well, it's got a speed of v at that point E, and therefore we have mv squared upon 2. And now, if we use the work energy principle, then what we have is initial EPE, so that's 4 mga, and then we add on 0 and another 0, and then at the end of it we have mga upon 4 and then we add on the EPE at the end, 3 mga upon 2 plus mv squared upon 2. So simplifying, noticing that the m's cancel as well, we have 9 ga upon 2 equals v squared, and if I square root V is equal to 9 GA upon 2 square rooted, and therefore the maximum speed will be, well, the square root of 9 is 3, and then we've got GA square rooted over the square root of 2, so what we end up with is 2GA square rooted over 2. Meters per second. Next, in reality this spring is not light. We have to state one way in which this would affect your energy equation in part B. Well, there would be a greater gain in GPE, and what that means is there's a less of a gain in kinetic energy, which means we would have a lower speed. Question number 8. Figure 5 represents the plan view of part of a smooth horizontal floor where R, S and ST are smooth fixed vertical walls. The vector RS is in the direction of I and the vector ST is in the direction of 2I plus j. A small ball B is projected across the floor towards RS. Immediately before the impact with RS, the velocity of B is 6I minus 8j meters per second. The ball bounces off RS and then hits ST. The ball is modelled as a particle. Given that the coefficient of restitution between B and RS is E, for part A we have to find the full range of possible values of E. Well, what we are told is the velocity before this impact is 6I minus 8j. So let's add that on. We'll call this velocity A, and it's equal to 6I minus 8j meters per second. Now, let's consider the first impact. Well, after the first impact, let's suppose that it leaves with speed B equals xi plus yj. Well, parallel to RS, nothing would change. So we have still remaining 6I. But then perpendicular to RS, what we would have is negative E, because it's going in the opposite direction, multiplied by negative 8j so what this is equal to is 8 EJ, and therefore B is equal to 6I plus 8 EJ. Now what we have to do is find a full range of possible values of E. Now what we know is this vector ST is equal to 2I plus j. And the way to think about this is the gradient of this line needs to be less than the gradient of this line. So what we can say is the gradient of ST is 1/2. For collision to occur, the gradient of B needs to be less than 1/2. Now, the gradient of B, that will be equal to (8e) over 6. And so, what we have is 8e over 6 being less than 1/2, which means E is less than 3 over 8. So the full range of values for E, we've got 0, which is less than E, which is less than 3 over 8. Now for part B, it's given that E equals 1/4 and that the coefficient of restitution between B and ST is 1/2. We have to find in terms of I and J the velocity of B immediately after its impact with ST. Now let's suppose this velocity is given by C. And let's suppose it's equal to lambda I plus mu J. We need to find out what that is. So, what we need to do is find a unit vector parallel to ST and a unit vector perpendicular to ST. And that would allow us to find out a vector here and here. So, if ST is in the direction 2i plus j, that means a unit vector parallel to ST will be given by 2i plus j over the square root of 5. And perpendicular to this, well, if I think about it, I want something in this direction here. So what that will be, it will go minus I plus 2j this way. When I take the dot product of these, I would get 0. So the unit vector perpendicular to ST will be given by minus I plus 2j over the square root of 5. So now what we can do, if I go back to the diagram, is find out a vector parallel to ST and then find out a vector perpendicular to ST, and adding up these vectors will give the vector C. So parallel to ST, well, what we would have is our unit vector 2i plus j over the square root of 5 dot product with 6i plus 2j, which is the speed of approach. That's what B is. And then what's happening is this vector is travelling in the direction of this unit vector. So I need to multiply by 2i plus j over the square root of 5. So what we end up with over here then is, well, here I've got 12 plus 2, and then that's 14. Root 5 times root 5 is 5. So I've got 14 over 5 multiplied by 2i plus j. Now, perpendicular to st, well, I've got this coefficient of restitution, which is 1/2. And remember, it's going in the opposite direction here. So we would have minus 1/2. The minus is because it's going in the opposite direction. And this 1/2 is the coefficient of restitution. And then what I need to do is multiply this by minus I plus 2j over root 5 dot with 6i plus 2j, and this is in the direction of minus I plus 2j over root 5. So if I work out what this is, well, here I've got minus 6 plus 2 times 2, so that is minus 6 plus 4, which is minus 2, timesing that by 1/2, we get minus 1, and then I've got the minus here, so that's going to give plus 1, and then I've got root 5 times root 5, which is 5, so I've got 1 over 5, and then I've got the vector minus I plus 2j. So adding those vectors to this diagram, what we can now do is find out what C is. C is then equal to the sum of those vectors. So C is equal to, well, in terms of the i's, I've got here 28 over 5 minus 1/5, so that's 27 over 5. That's in the I direction. And then I've got 14 over 5 times plus 2, so that's going to be 16 over 5. J. And therefore, the speed, well, the velocity is equal to 5.4i plus 3.2j meters per second.